reality, after many years of speculation and research, scientists have finally found the first ever white hole. What is a white hole? Why are astronomers excited about it? And how does the discovery affect you as a person? Stay tuned as we bring you the first ever white hole discovered by scientists. You have probably heard of black holes, terrifying massive objects lurking in deep space and swallowing anything that comes near. However, there is the opposite of the black hole, and it is called a white hole. A white hole is no less terrifying, but to understand it better, it's essential to know how black holes come about. And this is where we start from. Take note of the descriptions because many of them apply to white holes too, but in reverse. Black holes can come in a range of sizes, but there are three main types of black holes. The black hole's mass and size determine what kind it is. The smallest ones are known as primordial black holes. Scientists believe this type of black hole is as small as a single atom, but with the mass of a large mountain. The most common type of medium-sized black hole is called stellar. The mass of a stellar black hole can be up to 20 times greater than the Sun's mass, but are relatively small. They can easily fit inside a ball with a diameter of about 10 miles. The dense mass concentration is responsible for the powerful gravitational pull they exert on other objects. Scientists estimate there are dozens of stellar mass black holes within the Milky Way galaxy. The largest black holes are called supermassive. These weigh more than 1 million suns combined. However, they would fit inside a ball with a diameter about the size of the solar system. Scientific evidence suggests that every large galaxy contains a supermassive black hole at its center. The supermassive black hole at the center of the Milky Way galaxy is called Sagittarius A. It has a mass equal to about 4 million suns and would fit inside a ball with a diameter about the size of the Sun. Where do black holes come from? Primordial black holes are thought to have formed in the early universe soon after the Big Bang. Stellar black holes form when the center of a very massive star collapses in upon itself. This collapse also causes a supernova, or an exploding star, that blasts part of the star into space. Scientists think supermassive black holes formed simultaneously as the galaxy they are in. The size of the supermassive black hole is related to the size and mass of the galaxy it's in. A black hole cannot be seen because the strong gravity won't allow even light to escape it. However, scientists can see the effects of its strong gravity on the stars and gases around it. If a star is orbiting a certain point in space, scientists can study the star's motion to determine if it is orbiting a black hole. When a black hole and a star are orbiting close together, high-energy light is produced. Scientific instruments can see this high-energy light. Sometimes a black hole's gravity is so strong that it can pull off the star's outer gases and grow a disk around itself called the accretion disk. As gas from the accretion disk spirals into the black hole, the gas heats to very high temperatures and releases X-ray light in all directions. NASA telescopes measure the X-ray light. Astronomers use this information to learn more about the properties of a black hole. And here is a quick one. Will our Sun ever become a black hole? Not really, due to a limitation. The Sun is saved by not having enough mass to collapse into a black hole. But that doesn't mean it will escape death. When the Sun is at the end of its life in billions of years, it will become a red giant star. Then, when it has used the last of its fuel, it will throw off its outer layers and turn into a glowing ring of gas called a planetary nebula. Finally, all that will be left of the Sun is a cooling white dwarf star. But all this is still far in the future that it makes no sense to worry about it now. This brings us to white holes. A white hole is the exact opposite of a black hole. In fact, it is a black hole viewed backward in time. As stated before, once material reaches the event horizon in a black hole, the material is doomed and cannot escape its strong gravitational pull. In the same way, a white hole is a region in which space-time flows inexorably outwards. It is said to have an event horizon radius which prohibits the entry of any matter, including light. The white hole is believed to expel light, radiating at levels equal to the force of a black hole. If a foolhardy crew were to attempt to enter a white hole, the sheer force of the gamma rays would destroy them and their ship. But let's even pretend the ship was strong enough to withstand that amount of energy. Even at that, space-time around the white hole is structured so that the amount of acceleration required to get inside gets higher and higher the closer you get. In short, getting inside a white hole requires more energy than there exists in the entire universe, so you might as well not try. As you may suspect, the theory of white holes was first found due to the mathematical fascination with black holes. In 1905, Albert Einstein realized that although accelerating observers experience time differently, that does not apply to non-accelerating observers, those moving at a constant speed or stationary, and that the speed of light was independent of all motion. Einstein later published his theory of general relativity, which concluded that objects with mass have gravity, which is a distortion of time and space, rather than an actual physical force. Karl Schwarzschild would then use Einstein's field equations, solving them to find the equation of mass in empty spacetime, or an area completely void of all matter. This resulted in the Schwarzschild metric, which we will spare you as the equation itself is incredibly complex, but in simple terms, it is a mathematical representation of a black hole. Schwarzschild had created an equation of a completely static black hole with no charge or change. This is an external black hole, that is, a black hole that does not change in size and has always existed. Remember that at or beyond the event horizon, all events happen infinitely far in the future, so to an outside observer, these events never happen. The Schwarzschild metric shows us that at the idealized black hole, space becomes time and time becomes space, swapping their roles so that the singularity of the black hole is in some inevitable future time instead of a place. When reversing time in a real black hole, we see a dying star. However, when reversing an eternal black hole, we end up with a white hole. However, not all scientists agree that white holes exist, which makes the recent discovery about them even more significant. But why do some scientists doubt that white holes exist? Well, they claim that just because a white hole obeys general relativity and is mathematically sound doesn't mean it's practical. This is why some scientists call white holes an impossible possibility, meaning that while they can't be completely ruled out, they also don't expect to see one with telescopes. They base their thinking on the fact that this phenomenon violates the second law of thermodynamics, which says entropy in the universe must always stay the same or increase. Entropy is usually described as chaos, but can be better understood as an increase in how many states are possible for particles in a certain system. For example, think of a house demolished into rubble. It is an example of an increase in entropy because that rubble can make many other structures like sheds, bookshelves, mounds, and paper. However, a house is only one particular state of those particles. Now, small local decreases in entropy can occur as long as the universe's overall entropy is increasing. Black holes are excellent at this because they take matter low in entropy, such as planets, and disperse them across large spaces over time, increasing the chaos of space. But white holes, which eject matter, violate this law as they would decrease overall entropy. This is also why physicists argue that time cannot go backward. But this does not prove that white holes do not exist. Consider what theoretical physicist Carlo Rovelli suggested, that once black holes could no longer evaporate and shrink due to the constraints of space-time, the black hole would then experience a quantum bounce, or an outward pressure, and transform into a white hole. This means that black holes become white holes almost instantly they form, but as outside observers, we continue to see a black hole for billions of years because of gravity's time dilation. If this theory is correct, black holes that formed in the early years of the universe could be ready to die and burst into cosmic rays or another form of radiation at any moment, which we might have witnessed. Back in 2006, NASA's SWIFT satellite detected an exceptionally powerful gamma-ray burst named GRB 060614 in a very strange region of the sky. These kinds of bursts typically fall into any of two categories, short burst and long burst, and are usually associated with a supernova, but GRB 060614 didn't do either. It lasted for a remarkable 102 seconds, but was not associated with any star explosion. Most gamma-ray bursts, for comparison, last only between 2 and 30 seconds. GRB 060614 occurred in a galaxy with very few stars that could produce explosions or long bursts. It appears to astronomers and astrophysicists that this gamma-ray burst came from nowhere and collapsed in on itself after just a few short moments. However, some years later, scientists introduced the hypothesis that GRB 060614 could have been a white hole. Why did they come to this conclusion? It's because GRB 060614 describes perfectly what one would expect to see from a white hole, a mighty, unstable fountain of matter and energy that disappears shortly after forming, usually from a point too small to see. What makes this hypothesis strong is that current scientific models have no other explanation for what happened. Let's hear what you think of the existence of white holes in the comments section below.